start. So welcome to day 4 of Intro to Astra. No, not Intro to Astra. Day 4 of Exgal. What are we doing today? Today we're doing distances. I just read what's in front of me and say it out loud. Distances. So we're going to continue distances. It says it's wrong on the other one. Okay, so today we're going to post-mortem the homework. So I just want to go through everything and make sure that everybody gets all the little details and has a space to ask questions or complain if you're like, I didn't understand how to do that one. And then we'll continue our talk about distances. So let's start here. Oh, it still says paper sack on my door. That's gone. There's not a sack on my door anymore because I just started having everybody turn everything into Canvas. It's so much easier because, when I first started, there wasn't Canvas. There was only Blackboard, and it wasn't very good. So I just had people put answers in a folder on my door. But now last year, somebody kept putting their homework in there, and I wouldn't see it, and I would mark them late. And then it'd be like 3 days later, I'm like, oh, shit, there it is. So anyway, that's vestigial. Okay, so demonstrate that an unresolved binary of equal mass, the apparent magnitude is about 0.75 magnitudes brighter than either star individually. And I don't want a specific luminosity, I just want general things. So this problem, I realized this problem is tricky, and this is why I ask everybody how long it takes. Because it lets me know when, oh, hey, this one, I probably need to work on the wording of this, maybe a little. Because all of those words make complete sense to me, and I know what they mean. However, I took this class already, so that's not really very fair, is it? So I need to reword that first one. But what does it mean? So demonstrate that an unresolved binary of equal mass, the pair of stars is 0.75 magnitudes brighter than either star individually. So the hard part about this problem is just like, what the hell is that talking about? I think. You can correct me if I'm wrong, but I think that's the hard part. The math isn't hard. The math is pretty trivial. The hard part is, what do I mean by unresolved binary? Oh, I should put the camera on me. So that means a binary star. Most stars are binary stars. And most binary stars are triple stars. Stars like to form tight little packages. So really about half of stars are binaries. So most stars come in pairs. An unresolved binary, if I look at it in my telescope, still looks like a point. A star looks like a point in my telescope, regardless of my telescope, except for a couple stars that are really close, like the Sun or Betelgeuse, or I think Vega they have images of. But most stars you can't resolve. The actual star itself, it's smaller than whatever telescope you're going to throw at it. So stars are effectively zero-dimensional objects. As long as you're bigger than a star. If you are a star, then it has internal structure. But for everybody else, a star is basically a zero-dimensional object. So when I look at it with a telescope, it's just going to fill up 1 pixel in my detector. If I've got 2 stars that are real close to each other, they'll just both fill up that same 1 pixel if they're smaller than my angular resolution of the star. So I have my CCD. This is the cheapest CCD possible. It has 9 pixels. If both stars, so I have 1 star, it's going to drop its light into this pixel. It'll spread around and some stuff, and you'll have diffraction spikes and whatever, but let's pretend for now that everything just works. This star is just going to dump all its light into 1 pixel. If I have 2 stars and they're so close to each other that I can't resolve the difference, then I'll dump both of their light into that 1 pixel. So the answer is just, what is the total light coming off of 2 stars compared to 1 star in magnitudes? So the stunt have M2 minus M1. I might come up with a minus sign at this because now I'm actually I have the answer there. Yeah, let's do it that way. So M1, the luminosity of 1 star, is minus 2.5 times the log of its flux over F naught plus M naught. I don't care about those too much. These are the things that I care about. And if you omit these when you're doing it, I'm not going to be sad. But the important bit is the mass of one star is minus 2.5 times the log of its flux. The mass of two stars is going to be minus 2.5 times the log of the flux of two stars. How's the flux of two stars compared to the flux of one star? It's going to be just double. So this is just 2F over F naught plus F naught, whatever. So how do logs work? Log of AB, log of A plus log of B, right? So I can just disassemble what's on the inside of this log, and I'm left with minus 2.5 times the log of 2 minus 2.5 times the log of F over F naught plus M naught. This is just M1. And this number, minus 2.5 times the log of 2, is 0.75. So we're left with the magnitudes of 2 stars is equal to the magnitude of 1 star minus 0.75 plus, because that gives you a minus sign. Because the log of, sorry, that doesn't change something. And this is minus. 2 stars is brighter than 1 star by 0.75. You can tell that it's brighter because the number's going down. Does everybody follow that? Anybody have any questions about that one? Yeah.
I have a question about like unresolved binaries. If
Yeah.
they're like white in the sky, then how do you know they're binary?
Because you can. So that's a good question. So from the spectrum of a 2 solar mass star is different from the spectrum of a 1 solar mass star. So if I take a spectra of that unresolved binary, I will see, oh hey, that looks like a 1 solar mass star.
What if they're the same mass?
Then you'll see 1 solar mass. So you'll get the combination of the 2 spectra. So if they're exactly the same mass, you'll get the same spectra twice. So they will just add up on top of each other. If they're of different masses, then you'll get some slightly different combination of spectra that you'll be able to tell. The other way you can tell is by the Doppler shift of the stars. So if I have an unresolved binary, if I just park on it for a couple of days, the spectra will shift around, and you'll be able to see it.
I was gonna say, how do you tell the difference in spectra between just a star that's 2 solar masses and 2 separate 1 solar mass stars?
What is the big difference between, so remember what I said about a star. A star is a black body with an atmosphere, and I haven't said anything about atmospheres, so you can just remember that that's up there. So stars are black bodies. What's the difference between a 2 solar mass star and a 1 solar mass star as far as the black body that they're producing? Temperature. Temperature of a 2 solar mass star is higher than 1 solar mass star, so the black bodies they give you are different.
Gotcha. Yep, that makes sense.
See, and you can tell when you have a couple different black bodies stacked on top of each other. Yeah.
And when you have the binary star and you can't resolve it, can you still tell based off the Doppler shift of the frequencies that one's moving backwards and one's forwards?
Yeah. Yeah.
It does depend on the plane, right?
Sure does. That's a good point. So if the unresolved binary is orbiting like this, then you have to have the spectra, and you can't really tell. And sometimes if you don't have spectra of everything, it gets really tricky to tell. So if I'm doing photometry where I'm looking at colors of a buttload of stars at once, then it gets tricky to tell who's an unresolved binary and who's not. Yeah.
Is it more common for the stars to be like very similar mass, or one to be like really small in comparison to the other?
They're usually pretty similar. Which, I mean, they're not exactly the same, but they tend towards being similar. Usually if you have a big star and a little star, the little one will get ejected, because usually there's a third companion. When you have 3 stars is unstable. Not unconditionally, there are many triple systems out there, but a random 3-star combination is not stable. So as they're forming, if you form stars that have a bunch of different masses, usually you're going to have a big one and a little one and maybe a third one, and the little guy will get ejected from the tidal dynamics. Yeah.
How long, like, I don't want to say like on average, but like what's a typical like orbit period of the binary system?
That's a good question. It depends on the orbital separation, and it can go from minutes to thousands of years.
Wow.
So Proxima Centauri is the closest star to us. It's on an orbit around Alpha Centauri. Alpha Centauri and Proxima Centauri really just make up Alpha Centauri. It's a triple system. The closest one is on this 1,000-year orbit around the other two. So that's a triple system that's stable because I have a binary that's basically equal mass, and then I have this little guy that's way out.
Gotcha.
So that guy orbits on, and I think it's like 1,000 years or maybe 2,000 years. So even though it's in a binary system or a multiple system, that's going to be this closest star to us for your whole lifetime and your children and all that. So that's a good question. But then when stars will merge, so when they start to merge, they get really close, and as they get close, they can orbit on the periods of days, minutes, maybe not minutes, hours. Black holes, when they inspiral, will oscillate at audible frequencies, so kilohertz.
Are they on Alpha Centauri? Are they like on the main sequence, or what kind of stars are they?
Yeah, they're main sequence stars. They're all three are main sequence stars. I think they're all still on the main sequence. Yeah, good questions. And we think that Proxima Centauri has a planet in the habitable zone, which is pretty friggin' dope. But it's a little star, and little stars are really magnetically active, and so they're really X-ray active. So this is a little star that's just bathed in X-rays from the sun. So that would make it hard for life to form, but I guarantee not impossible. So if I could answer one question, like in my whole life, it would be, is there life on Proxima Centauri? Because it's right there. I feel like there has to be. Anyway, any other questions on binary stars?
The closest planet system that happens to be just right.
Yeah, I don't know if it's just right, but it's in the place where it can have both liquid water and ice. So that's.
Seems like a lot of coincidence, though.
No, it turns out that it's actually that is the dominant. That is a thing that happens. It's not a coincidence. That happens all the time. Like half of the stars in the Milky Way have planets in the habitable zone. And there's like 100 billion stars in the galaxy. So anyway, people ask me if I believe in life on an outer space, and like there's no possible way. What's the probability of forming life on Earth? If it's 1 in a billion, then we have 100 planets with people on it. So anyway, okay, let's move on. Crowther found this star, 260 solar masses. I gave you two age estimates, an easy one and a complicated one, and you just need to drop that mass into that expression and get a number out. And you should get 9,000 years for the cheap one, which is basically instantaneously in astrophysics, or 200 or about 2 million years for the more complicated one, which is more accurate. So big ass stars live for about 1 million years, 2 million years.
Yeah, I got that. I'm like,
I thought it was
this is
either
wrong. I
one.
thought it was wrong because I'm like, this is so very different. I'm like, 1,000 years, like a couple thousand years is nothing. Like, it's
Yeah,
can't be right.
10,000 years is not very long. That's not a right solution. And that's part of why I do it. Is we'll use this these mass power laws all the time for the main sequence lifetime, and they get you kind of there, but there's the better approximation. Use the better approximation when you have bigger stars. Works pretty good for little stars. But so 2 million years. Okay, what is the most massive star that is still on the main sequence? How big is it? What'd you get?
0.8.
You get about 0.8. And that is the canonical value that everybody will quote you. You ask an astronomer what's the oldest stars in the universe, they'll tell you 0.8 solar masses from the same argument. What spectral type is that?
Okay.
Probably K. And tell me about what those stars have contributed to supernova in the universe. Nothing. Why? Because none of them have exploded. So it's kind of a sideways question. The answer is none. None of them have exploded. They're all still on the main sequence. That's
Aren't
the
they
whole
also
point of the
just
question.
too small? Like I thought.
Well, so then the second question is what happens to a solar mass type star after it dies? So what happens to a solar mass type star is it goes through a planetary nebula phase. So the engine at the center breaks down, and it belches out this enormous, gorgeous planetary nebula, and it sheds all of its a huge amount of the outer layers of gas, and it becomes this planetary nebula. And the center bit becomes a white dwarf. That white dwarf can do one of two things. It can either sit there forever and not do anything, which is probably what they do, or if there's a companion and it can accrete mass. If it can suck mass off of a buddy, there's a couple different ways to do that. If you can get bigger, then so you can do that by either colliding two stars, which happens plenty, even though I said they're zero dimensional, they still collide plenty. They're zero dimensional, but they have a big cross section because gravity falls off like 1/r squared, right? So if you have a 0.8 solar mass or a 1 solar mass star, and it either runs into another star or can accrete material from a companion. If you've got a companion here and a little star over here, this one will be blowing winds, and that winds will land on this other star. Once that star gets above about a solar mass and a half, it'll explode as a type 1a. If that doesn't happen, it won't explode. Well, one thing that could happen is it slowly accretes stuff, and if it's accreting material too fast, then it'll be a classical or a repeater nova where the surface just blows up periodically. But if it accretes it at the right rate, then the whole thing can blow up. But none of these have done that yet. They're all still on the main sequence. Okay. Because it needs to be a white dwarf before it explodes. A main sequence star, it accretes more mass, it just becomes a bigger star. Once it's a white dwarf and it's crazy dense, like nuclear density, like the neutrons are bumping into each other kind of thing. Once it gets that dense, you put a little bit more mass on it, then the thing explodes. We'll talk about that in a minute. Let's see. Two open clusters. Which one's older, the yellow one or the blue one? The blue one. Why? Because the turnoff point is the important bit. Now, these are not shifted relative to each other. They're at the same spot, and just one has had the high mass stuff peeled off. So when you think about this, think about two dudes that are like that, but one of them has some of the bits blown apart, like getting your fingers cut off or something. So it's just the big things have blown up. So this one is younger because it still has all these big guys that haven't blown up yet. It has these guys are starting to blow up in the yellow, just like these guys in the blue. So this is transitioning to the post-main sequence stars, and these are post-main sequence stars. Now let's see. Is that 4? Are we on the hard one? Okay, so it's short, and you should get 4 and minus 27, or 4.7 and minus 27. And I think, for the most part, I think everybody got that. Alright, so, oh man, did I leave the map for myself in the slides so that I don't have to remember anything right now? Aha, I did. Yay. How did I just lose the job? Okay, so how do we do this one? So the question is, get the magnitude of the sun, both the apparent magnitude and the absolute magnitude, from assuming it's a black body. So this is like basic physics turning into measurable astrophysics. So what do you first do? So we first start off with the spectrum. So the black body is this thing. I always screw up the H's and C's. 2hc squared over lambda to the 5th times 1 over e to the minus h c over lambda kt minus 1. And this is, in units, is in ergs per second per centimeter squared per wavelength per steradian. So, what do you do? So the first thing that you do is you derive the Stefan Boltzmann. So you integrate b nu of t with respect to, let's start off with the surface area. This doesn't depend on the geometry of the star at all, so I can just do the surface integral. The b comes out, and I'm just left with a surface area of a sphere. So this just gives me 2 pi r, 4 pi r squared times the black body again. Then I got to integrate over solid angle. And this integral has a cosine in it because you're integrating from the North Pole down. You're integrating from what you see in the sky. So it's again b nu of t times d omega, but d omega is cosine theta d theta d phi, and we integrate theta goes from 0 to pi, and phi goes from 0 to 2 pi. And so what you're left with when you do that integral, it just picks up pi. Yeah.
I think this all should have a sine theta.
Oh, yeah, sorry. Thanks. That's what it says up there. Oh, and you get a cosine theta from the other integral. Anyway, you got to do those integrals, and you're left with the solid angle integral just gives you a pi. So we're left with, after doing the area integral and the solid angle integral, we're just left with 4 pi squared r squared times the black body. Now this is again a spectrum. This is a function of frequency. So this doesn't give us much yet. But it does tell us how the spectrum of different stars is going to behave. So if I have a bigger star, the frequency, the spectrum just goes up if the temperature is the same. And that's the thing stars do. Stars change size throughout their lifetimes. Everybody good with this? Just 2 integrals over geometry.
It's just the pi squared, right?
Yes, 4 pi squared r squared comes from these 2 integrals. Then we got to do the integral over the black body. And I gave you the integral, and I apologize, I forgot to put it in the homework. I need to put that integral in the homework. Because I don't think everybody has that one, like, on the tip of your tongue. 0 to infinity of x cubed over e to the x minus 1 dx equals, is it pi squared over 15? Pi to the 4th. Okay, so here's an integral that you look up in an integral table. There's maybe a good way to do that. I don't know how to do this one off the top of my head. But I need to make that look like this. So how do I do that? What's the hard part of this integral? The hard part of this integral is this e to the x. So I need to do a u substitution with whatever is in that e to the x. That e to the x is minus hc over lambda kt. So we'll do u equals minus hc over lambda kt, which if you're missing a minus sign, that's where it was. Yeah.
I think that was positive.
What?
The e to the negative is
This?
in the slides it said positive.
Oh, that's a typo in the slides.
Oh, it's a typo.
Yeah. Where in the slides?
We're right there.
Right there, it's wrong.
No.
We had definitely notes as well.
I might have 2 typos. I will double check that. Yeah, it has to be a minus sign because of physics. And also, otherwise you get a negative number here. So I apologize, there's typos in the notes from time to time.
I did it with a positive one and I got a positive number.
Okay.
I don't know if it's
When you do this part, when I get du equals is minus hc over lambda squared kt d lambda. When you did this part, you might have dropped a minus sign because the d lambda gets a minus sign. That's a common place for a minus sign. Regardless, these are all like little details. That's okay. You got the basic idea. That's really what I care about. So you do this U substitution. I get a lambda squared here, which cancels some 2 of my lambdas, and then I'm left with this integral. So you just need to take these units, don't screw up the U substitution, and plug this in, and then you're done. Watching me do all of that is not instructive. Yeah.
Could you say that?
Yeah. You've got your units. Or your units. Those come out of the integral. So I just left with lambda to the minus 5, and then this business. When I do the U substitution, I get an HC and a lambda squared, which cancels out 2 of my lambdas, and I'm left with just x cubed. And then I just have, and then that integral turns into this integral, and I'm left with the units that I had here and the units that I had from the U substitution. So then you get the Stefan Boltzmann law. Oh, I didn't write it down. And my memory is terrible, so I don't remember exactly all the pi's and stuff. So you're left with, oh, that should be an r squared. 4 pi r squared times this number, which is a combination of h's and c's and stuff. The Stefan Boltzmann constant times 2 to the 4th. So now we have the luminosity. Now what do we do? Now we want to turn that into magnitudes. Let's see. So we know the temperature of the sun. We know the radius of the sun. We can just plug those in. Let's see. So you should get that the luminosity is like 10 to the 33 ergs per second. Now you can compute the flux at 10 parsecs as this by just dividing by 4 pi r squared, 1 AU squared. But you don't strictly need to do that. So you can, since we're taking a ratio, so the apparent brightness the absolute brightness is just the luminosity over that of an A star, which gives you, which you can look up, which gives you more 4.7. And if you use the distance modulus, little m minus big M is 5 log d over 10 parsecs, you get the apparent brightness of minus 26, like minus 27. So minus 27 as a brightness lights up the whole sky and gives light to Earth. So that's a really damn bright object. 4 is like a star that you can't see all that great. Okay, anybody have any other questions on that? Feel pretty good. When these show up again, we can talk about them again. I got 30 minutes, not bad. Oh, okay. So I'm going to go back to reddening. I'm going to pick up there. So let's talk about that again. Here, we'll start here. So the apparent brightness is little m minus the reference, because minus 2.5 times the log is 10 of flux over the reference flux. Now, if the thing gets further away, another way to think about this is, remember, flux is luminosity over 4 pi times distance squared. We can call this luminosity over 4 pi d squared over f naught. So if d goes up, the thing gets dimmer. But if I have dirt in the way, the thing also gets dimmer. So we fix this up and we say, I'm just going to put in a fudge. It's just a thing that represents the things that I don't understand. So we say instead, little m minus the reference is minus 2.5 times the log of the flux, not plus a. Why a? Because it's the first variable, and this is one of the most important things that we have to horse around with as an astronomer. A is the extinction. It is how much dimmer a thing gets because there's stuff in the way. A doesn't depend on frequency. A is everything. However, some things do depend on frequency. So color depends on frequency, but color doesn't depend on distance. Why? So okay, remember a color looks like a B minus V. There are many colors. Oh, let's talk about that for a second. There are many filters, and there are many colors I can make. I can do B minus V. I can do B minus R. The bluer one always comes first. So the shorter wavelength filter always comes first. Lower numbers in colors are more blue. So a lower color means it's more blue. That's how colors are defined. Now I can define B minus R, or U minus V is one that's pretty common. And these are just filters that are centered at different frequencies. So I say B, I just mean a frequency that's centered at the blue colors, and R is the red colors. This is set at like 600 nanometers, and this is like 700. So we take the difference in brightnesses. Remember that these two guys are in magnitudes. So B is the B band flux, R is the R band flux. So we take the difference of these two guys, and we're left with the log of stuff. So B minus R is equal to minus 2.5 times the log of the blue flux minus the red flux, plus other stuff that are just numbers that you look up. Don't screw up the algebra. I trust that you guys can all do algebra. The other stuff is the F naughts and the other constants that are all like zero, and they're all just things that you can look up. The relationship that we care about is B band flux minus R band flux. So this difference is a ratio of what I actually measure with my telescope. I can rewrite this as minus 2.5 times the log of the luminosity in the B band, which is then going to be divided by 4 pi d squared. The luminosity in the B band, 4 pi d squared. These 4 pi's and the d cancel. So I could just call this the luminosities. So flux is what I measured, it's spread out. Luminosity is at the source, it's all the stuff, it's not spread out. So color doesn't depend on distance, so that's very, very useful. Because if I measure the color, I can learn about the object without knowing how far away it is. Yeah?
What did you say after
This is a squiggle. It's a technical term for all the crap that I don't feel like writing down right now. Because that's not the stuff that I want to talk about. Okay, I can write down exactly what it is. So it is exactly minus 2.5 times the log of F B naught, and that's a plus sign, over F B naught minus B minus V for an A star. So it's just the fluxes that are left over from this being a magnitude, and the offsets that are left over from these guys being magnitudes. So everything looks like this guy. Maybe you can so we can use that because we want to know how much dust. So we got to sort out how much dust, and then we say how much dimmer it is because of that dust. And we'll do all of that in one step by multiplying by 3. So it's a little bit of a dodge, but it works pretty well. So we define this thing called the color excess, E V minus V, which is kind of a complicated looking glyph, but this is just called the color excess. And it is B minus V, the color that I measure, minus V minus V without the dust. So the So to measure the color excess,
Are we like? Is there a reason why we're changing like R to B when it's like are we doing B minus B or B minus R or is it?
it is generic. You can just go through the whole lecture that I've done and swap all the colors around. It doesn't matter. I use B minus V a lot because it's a very easy color to get. But I can change V to R, B to U. Lots of different filters that I can put in this combination. That's a real good question. Because I will generalize this, and other people will generalize this to be, you can have a U minus V color excess, which would look just like this. Just swap this with U and V, and this with U and V without the dust.
And the swapping the colors correspond to specific like polarization of the light in the filter?
Not polarization, frequency spreads. We're not going to talk about polarization at all this semester. If you're interested, you can get me talking about it during office hours, but it's a deep rabbit. So the only difference between B and V is where they are. B is like here. B is like here. R is like here. U is like here. That's an SDSS, a Sloan filter. So different telescopes, all the different telescopes have filters, and some of them are the same, and some of them they build just for that telescope. So there's lots of different filters. There's lots of different pieces of colored plastic that you can find. They're just pieces of colored plastic, and you can find lots of pieces of colored plastic. They're very specific, so they have very the right wavelength coverage. Okay. I'm going to put all this in a color magnitude diagram. I'll leave that up. Let's talk about a color magnitude diagram. Oh, right, I forgot this board sucks. That gets stuck over there. Only goes like half apart. One of these days, I'm going to come down here with a wrench and rebuild this board so that it does what I want. Okay, so this is a color magnitude diagram. So here we have temperature or color. Let's call it B minus V again. But you could have other colors here depending on what you're doing. And on the vertical axis is the total brightness. Usually in one of these, but not always, depending on what's easy to measure for that object. Now, the main sequence kind of looks like this. Temperature goes up this way. Brightness goes up that way. So hotter objects are this way. How do I remember that hotter objects are backwards on the color magnitude diagram? Because lower numbers of colors are more blue. Lower number, more blue. More blue, more temperature, right? How do I know that? Because I know that my black body has a peak. The peak is some number, 2.9 millimeters, over the temperature in Kelvin. So as the temperature goes up, the peak of the wavelength goes to smaller and smaller and smaller and smaller wavelengths. 2.9 millimeters is pretty big for a photon. 1 is pretty cold for anything. So T is usually like 6,000. So 2 over 6,000 gives you the peak of where the sun is. A hotter star is 40,000. That would be a much shorter peak. That's a much bluer color. With much more short wavelength photons. Okay, that's kind of a distraction from where I'm actually getting, but I wanted to make sure that I said that at least once. I might need to say it a couple of times because I always have a hard time orienting myself with these HR diagrams until I think about what the physics is that's going on. So what does this main sequence tells me? What does the main sequence tells me? The main sequence tells me that hotter stars are brighter than colder stars. That's the first thing that it tells me. It tells me a lot of other stuff because there's a lot of other things that go on in stellar population diagram. But I'm just going to talk about dust for a second. So now, if I have if I have a main sequence population for a bunch of stars, it might look like that. Another one that's further away will look like this. It'll be basically the same, just shifted down as it gets dimmer. Does that make sense? What happens if it gets redder? Where does the line go? To the right. So if it gets redder, I'll use the red chalk. It goes that way. Now it's not going to get redder and not get dimmer. So this will actually be down like this. So distance just makes vertical motions. Color makes left and right motions in the HR diagram. That's useful because then I can sort out how much, so I know where the main sequence is supposed to be, so I measure where the main sequence is, and then I say, okay, some of this motion is dust and some of this motion is distance. So we can sort out what's what. How do we do that? So what we do, so I'm going to call this AV for the visual extinction. There's lots of extinctions. It's either A for the total extinction or AV for the visual extinction. Basically the same object, it's just whether or not I remember to write the V. The visual extinction is up and down, and not left to right. Color excess is left to right. No, let's just say right. I'm not going to say never have a negative color index or color excess, but I don't know what you would do. You would have to like inject more blue light, which is a hard thing to do. So in the HR diagram, further away gives you AV, which is up and down. Or sorry, let me do that a little different. AV does that. Distance is up and down. Color excess is left and right. But it will also go down because there's also a blocking of this stuff. So what we need to do is sort out how much of this motion comes from it going over this way, so that we know how much is going up this way. Does that make sense? So what we say is AV, that's the up and down, is equal to some number R times my color excess, EV minus V. So this is all light, this is just the blue light. And this R is a number that we got to measure. And we hope that it's generic and we can use it for a bunch of different systems. It isn't, and we can't, but we do it anyway because we're astronomers, and sometimes when you have no options, you do a kind of crappy option instead of giving up and going home. So R is 3.1 for most of the Milky Way. It's different from other galaxies, and sometimes if you're looking at like the center of the galaxy, it might change. So if you're looking right at the center of the galaxy, we'll talk about what's in the center of the galaxy in a couple of days. Okay, so usage. Leave you over there, and you. Monorace. So how do we use it? I got slides on this. That way I don't have to type everything. Let's see. So I went through this on Tuesday, and now I'm doing it again. So, for instance, Andromeda has a measured visual magnitude of 3.4, has an absolute brightness of minus 21, which is, that would light up the sky. Also, we'd be in it, so it's kind of a dumb thing. Just saying the difference here gives you about 1 million parsecs, but if you add in the extinction, so you measure the visual extinction, and this is measured at, or sorry, the color excess is 0.16. We get the visual extinction by just R times 0.16 gives me 0.048. And then I drop it into here. Oops, go away. And I get the more accurate value of 0.75 million parsecs. I do this with all kinds of stuff. Let's see, is there anything else in here that I want to talk about? So this is lecture 3B, which goes through this rendering a little better. It has this table of colors. More blue, more negative. Hotter, more blue. Color excess, extinction, reddening, distances, blah, 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 blah. Oh, let's talk about what dust is for a second. This is why I run through these to get to these slides. This is kind of an awesome thing. This is a piece of interstellar dust that they took a piece of very low density foam up to this space shuttle and held it out the window. And this low density foam catches little pieces of interstellar dust as it passes through. It has to be low density foam because you want these things slowed down really gradually because they're moving at like 30 kilometers a second. So if you put something hard there, they will just become vaporized and all you will see is a smear of carbon and not know anything about it. They use this real low density foam to capture this thing. So this is like a few microns apart, so this is a couple thousandth of a millimeter apart. They're kind of blobby. So so some of you asked, how do we know about interstellar dust? This is one way, is from this sample return mission. It only tells us about the dust around the solar system. So that's one thing. But it does tell us about dust in outer space. It doesn't tell us about all the different kinds of dust, because different environments make different kinds of dust. But that's what it looks like. Here is a really nice image. I think this is in the book. This is B68, which is a dark cloud. And here, this is a 3-color image, B, V, and I. Here are the here's an A star and the filters. So this is B, V, and I. And you can't see through it. But if I use B, I, and K, K is way over here, and then you can see through it. That's kind of awesome. So we use these longer wavelengths to see past the dust. So the dust is blocking out mostly the visual and the near infrared. The further infrared signals go right past the dust. So we can see through it like this. So then I measure, what do I see in this image versus what do I see in this image? That gives me the color excess. Or what do I see in this population of stars versus what I know a population of stars should look like? Then I can get the color excess from that. For you, I will just hand it to you or give you a pretty straightforward way to get the color excess. More filters. No, I'm zoomed way too far out. Oh, I was going to talk about that. Do I? No, I'm not going to go through that right now. I don't need it. Anybody else? Here's another thing that you can use this business for. If you have a pulsating star, you have to take care of the extinction as well. So I've got a pulsating star. I have to worry about how much dust is between me and that star. So you look at the star, you know what type of star it is because you can see it. You can see it pulsating. You can see what kind of star it is. So you can sort out the color excess, and then from the pulsation period, you know what the intrinsic luminosity is. So that gives you the distance. The intrinsic luminosity doesn't give you the dirt by itself because the dirt and the distance are degenerate. Okay. All right. Oops. Okay, so variable stars. So these are three three different measurements in three different bands. So these aren't spectra, these are observations through filters. This is with the blue filter, MB, the visual filter, which is like green, MV, and the infrared, which is MI, which is like red and a little bit long of red. And you get slightly different physics because what you're looking at is a variable star. What a variable star is this pulsating guy. I think I went through this on the first day, but I'll say it again. You have a star that has some dirt in the atmosphere, dirt molecules. And when they're spread out, the light goes right through. And when the light leaves, it can cool. Actually, I have this in a... I thought I had it in a... when it shrinks, the density goes up. And when the density goes up, it gets more opaque. And as it's more opaque, photons can't get out. So the photons will just heat the star, which will make it expand. As it expands, it gets less dense, it gets less opaque, the photons can come out again, it can cool, then it can contract. And then keeps this cycle keeps going on and on and on for thousands of years, yeah.
How common is that?
They're all over the place.
So it's always not
It's not happening in all stars. So these only happen on, so if I've got my HR diagram, my HR diagram has the main sequence here. This only happens for stars that are up here off the main sequence. So once they leave the main sequence, then they get big and fluffy. And when they're big and fluffy, they're more susceptible to compression and all these things. How do I know that this star is bigger than this star? This star right here versus this star right here. In this HR diagram, I didn't label my axes, which you should always label your axes, even if you know what it says. This is magnitude versus color. So if I have these two stars, let's say I got these two stars and they've got the same color, which one's larger physically? I got this guy and this guy. The one with the higher magnitude, because the luminosity goes like the radius squared. And the color just goes like the temperature. So this guy's much larger. So these big fluffy dudes, these big fluffy boys, can do this pulsation. But not all of them. So there's a whole slew, hundreds of different classifications of stars up in this post-main sequence region. That's a super good question. So we get this formula that looks like this one says MV, this is the absolute brightness, is -3 times the log of the period in days. And then there's a correction plus some number. I don't know what that number is. I mean, that number is -0.8. These numbers all are measurements, so they all have error bars on them. But this is just the normalization of the period. So this is how bright it is, and this is how it varies with period. So you'll have a relationship like this. The period is the thing that you measure, and you drop it into here, and you get the total brightness. Here's a little bit of algebra. So this time, the sound crossing time scale, that's how long it takes for sound to cross the star, is just going to be the size of the star, R, divided by the speed of sound in the gas, C. The sound speed is also the temperature. So temperature is the sound speed squared. There's a K in there, but it's just a number. Temperature is sound speed squared. Units, got to get you the right units. Good. A way to think about that is thermal energy is KT. Kinetic energy is 1/2 mv squared. And those two things are equal. So from the virial theorem, we have GMM over R is KT. So this is the binding energy of the object, GMM over R. That's the energy. And then KT is the thermal energy. There's a factor of like 3/2 in there that we're kind of thrown out because they don't matter so much. So you plug everything together and that you get the period, P, goes like 1 over the density. So we're 1 over the square root of the density. So denser stars have shorter periods. So supernova, I'm going to spend a minute talking about supernova. Have you guys seen a chart like this? Did hopefully I put one up like this? Okay, so it's an observational classification. 1A are the only white dwarfs. 1B and C, all of those other guys are all bigger. So everything that's lower than 8 solar masses winds up in this red channel, or nothing. Everything that's bigger than 8 solar masses winds up on one of these core collapse sides. That's an oversimplification. There's probably more granularity in there. But the question is basically, okay, I have a supernova. Does it have hydrogen or not? So if it has hydrogen, then you know that it's still got a bunch of hydrogen in there. But if there's no hydrogen in the spectrum, there's probably no hydrogen on the star. So that means something that burnt for a long time and then got rid of all the hydrogen. Either it ate it or it blew it off in a wind. That is where these planetary nebula go. The planetary nebula is the star losing all its hydrogen, all the excess hydrogen and helium, and whatever else it has in it. Then you're left with something that doesn't have any hydrogen. That guy can blow up as a type 1A. Here are some planetary nebula. So this is where all the hydrogen goes when this thing is in its death throes and spazzing out stuff. They're beautiful. They're really fabulous. There's really super interesting like physics that you can sort out. Like some of these have hourglass shapes, and you can say, well, there must have been a ring there. They're really cool. I don't spend very much time with them, but they're very cool things. Let's see. I think I said all this. Yeah, so unless something happens, it'll just sit there forever. But if you can make the mass bigger, either by running into another star or absorbing material from another star, then that carbon and oxygen white dwarf can explode. And the carbon and oxygen all starts to fuse all the way up to nickel. And it's not a direct one-to-one where I take carbons and I make nickels. There's a complex dance of nuclear physics that takes you from carbon and oxygen to nickel. And it releases a buttload of energy and unbinds the star completely. So all of the star is gone after the type 1A supernova. That's not true for core collapse supernova. Core collapse supernova come from bigger objects, but they're less violent explosions. You're always left with, from a core collapse supernova, something left over, a neutron star or a black hole. How does this work? Did he talk to you about degeneracy pressure? Okay, so electrons hate each other. So if I have 2 electrons, I can't put them in the same energy level. That's called the Pauli exclusion principle. So I got to have an up and a down, and then I can have 2 electrons in the same energy level, but then only 2. So you learned that when you were learning the orbital structures in chemistry and stuff, but you'll learn this again when you get to StatMech and quantum mechanics. If I have a buttload of electrons, the same is true. They all have different energies zipping around. I can only have 1 electron with that energy. So that's okay. That just gives me a very specific way of ordering all the electrons. The electrons all get into this very dense block. And I got neutrons and free electrons. This thing is like 10 to the 9 degrees. It's very hot. So there's no atoms. Everything's ionized as hell. So I've got a bunch of free electrons and a bunch of free protons and a bunch of carbons. So the electron degeneracy pressure is really what's holding the star up. And when it gets too large, there's a certain limit to what the degeneracy pressure can do. And once your density gets higher than that, then the fusion starts to happen. And once the fusion rate gets faster than the rate you can get rid of the energy, then it blows up. I'm not going to test you on any of that, but the important bit is the explosion comes from what electrons are doing, not from this bulk star. It doesn't care about the total mass of the star, it just cares about the density in the center. And some other things. Peter might get mad if he heard me say it quite so simply, but that's basically it. Sorry. So because it's just supported by electrons banging on electrons. If I have more mass, I'll have more density in the center because it'll get crushed, and I'll have more electrons banging on more electrons. But it's still just the electrons banging on the electrons, or the electrons banging on the neutrons, that really matter. So that gives me a really specific threshold for when the thing's going to blow up. Once the density gets high, and for the density to get high, the total mass has to be larger than 1.4 solar masses. This is called the Chandrasekhar mass. And I'm not going to write down Chandrasekhar because I'm certainly going to spell it wrong. Actually, I'd probably get it right. I've written it down. Chandra was a super important scientist that did all kinds of stuff on all kinds of things. One of the things he did was he said, okay, this is what you can get from electron degeneracy pressure, 1.4 solar masses. And once it's a little bit bigger than that, then it's going to blow up. White dwarfs basically all do that. So they all look the same because it comes from microphysics and not anything about how much dust or how many planets the star had or how long it took to form or how the star was feeling that day. It doesn't care. It only cares, is the mass bigger than 1.4 solar masses? Once it does that, then it explodes just like this. So they all do the same thing. They all do this. Well, okay, not exactly this. They do a family of things that look like this. Some of them go a little slower because they're a little bit more opaque and it's harder for the photons to get out. So they decay, so they're a little bit less bright and they decay a little bit slower. That is where the microphysics or the details of the star come in. How much dirt was there? So how much can the photons get out? A little bit dimmer star decays a little longer. So we have this relationship. So let me talk about this curve for a second. So this is B magnitude versus the day. This is Julian day, blah. I'm not sure what that's from. I actually don't remember what that number is relative to. But this is in days. That's what JD stands for. And this is days since something interesting, but I'm not sure what. So we go off here at 360, and then 100 days later, so that's like 3 months later. So a couple days later, so we first start seeing the thing getting brighter, and then it gets really bright. And this is so bright, it's brighter than the whole galaxy that it's in. These are really, 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 really bright objects. So then once it reaches its peak brightness, then it's expanding because it's an explosion. It's expanding, so it's cooling. As it's cooling, it gets dimmer. Other things happen too, but that's the important bit. As it cools, it gets dimmer. So we have this big explosion, it cools and gets dimmer. So the rate that it cools and the maximum brightness are related by this relationship. So this is what we call the peak is 0, and then we go out 15 days after the peak, and we measure the brightness decline. So the decline after 15 days is called delta M15. M for magnitude, 15 for 15 days. So delta M15 is what you measure off of this star. And this guy, Mark Phillips, who's at Berkeley now, super important astronomer, realized this relationship that the peak luminosity is minus 21. Yeah, remember, this is a very bright object. Sorry, squirrel brain had to work through a couple things. This is the absolute brightness. So this is at 10 parsecs. And that's minus 21, which is the brightness of the sun. Remember how much dimmer the sun got when you put it at 10 parsecs? It became a thing that you couldn't really see. If this was at 10 parsecs, it would light up the sky. It would totally hose us. It would be really bad. But, so this is a very bright object, plus this linear, it's just linear in delta M15, which is really nice. MB is just minus 21 plus 3 times delta M15, and this lets you sort out the maximum brightness of that object, where it was. Then you got to correct for the dust, then you know the distance to the other side of the universe. So this is a very cool thing. How am I doing? I got 15 minutes left. Okay, so those are the ways. Okay, let me go back up to. Yeah, so we can use the distance modulus and this dust correction and this reddening stuff. All those things come together. If I'm going to use photometry, if I want to use the distance modulus to sort out how far away an object is, I also have to take care of the dust. You always have to do that. But we can do this for individual stars and pulsating stars. Individual stars are tricky. It's easier to do it with a population of stars. One star is pretty tricky because it might be dirty or have planets or be in a bad mood. You can do it on pulsating stars. Those are real good. You can do it on supernova, which are real good. You can see those all the way across the universe. You can do that on other objects too. I'm sure. I can't think of any that I care about right now. But so the first way we dealt with distance. Let me go back to my original slide. So we can measure distance with geometry. That was parallax, binary stars, and the moving cluster technique, which you can totally forget. But parallax and binary stars, I want you to understand. We can do it with photometry, and that's measuring the light. That's using this distance modulus. So that's measuring photons. Or we can do it with the velocity. And that we do, where do we go? There you go. Is that it? Oh, yeah. So, okay, this loops. Watch 2 points here. Pick 2 of these stars and look how fast they expand. And then pick these 2 points that are far away from each other and watch how much faster 2 points on opposite sides of the sphere are going relative to 2 points that are close together. Velocity is proportional to distance when you have something that's expanding uniformly. So we can see this in outer space. So v equals h naught d. So velocity is proportional to distance. That's what I just said. And we call the proportionality constant h naught. H is for Hubble because he's the first one to discover this. And here's his original discovery plot, which has distance on the horizontal axis and velocity on the vertical axis. That upper number, I don't know if you can read it, is 1,000 kilometers a second. And this one's a more, I think that's what that says. But anyway, so h naught is 100 kilometers per second per megaparsec. That's a weird unit, isn't it? Kilometers per second it's a distance per time per distance. Why do I do it that way? Because I'm going to take megaparsecs and I'm going to multiply this number by a number of megaparsecs, and I want something in kilometers per second. The kilometer per second is the default velocity unit for astronomers because things are going really damn fast. Think about how fast a kilometer per second is. I mean, it's ridiculous. So anyway, h naught is 100. That's a lie. But for a long time, it was really hard to measure what h naught really is with much accuracy. So 100 is a good guess. Now all of our distances are tied to this number, which we have to measure. So, and it turns out that it's not 100. It's 68 or 72. Maybe one of those two numbers. So use 70 for now. If you need to, use 70. And so we have this funny, and this will come up again later, but I'm saying it now because it's going to be fresh. And then in a little bit, you're going to be like, what the hell is that little h? And I'll be like, remember when I said, and you'll be like, no, I don't remember that. But that's okay. So if I have a distance to say, not Andromeda we measure with Cepheids. It's really close. But M51, which is pretty far away, if I measure the distance to M51, it's the velocity over h naught. Now, I don't actually know what h naught is, but I know it's like 100. So I'm going to say that this is v over 100 kilometers per second per megaparsec times this number little h. So when and this is in kilometers per second, and this is in kilometers per second, so my distance to say M51 is going to be something like 37 h inverse megaparsecs. Because I measure the distance using the velocity, but I don't actually know h very well. So we write down the distance as 37 times h inverse megaparsecs. H inverse goes with megaparsecs. It's kind of part of the unit. It's how we tweak the units for when I wrote a paper in the 70s. I want to compare to it to now. I don't have to go redo all their math. I just turn this knob. I could just retweak the cosmology by turning this knob. So what is h? The numerical value of h, you can all sort it out from here. I tell you, the actual expansion is like 70. I'm using 100, so h is like 0.7. We're not going to see this for a couple of weeks, but I wanted to say it now because it will show up again. But this is how we do this. So I take a spectra, I measure the velocity. How do I measure the velocity? I measure the velocity with Doppler. The fractional change in a frequency, so this is just how far did the thing move relative to itself, is how fast is it going, how fast are those photons going relative to, or how fast is the thing going relative to the photons. So we get the velocity from the frequency shift, and then you get the distance from the velocity, and you got to take care of h inverse because we don't really know. What does that look like? Why do I say, let's talk about h naught for a second. So this is the measurements of h naught as a function of time from when I started grad school to today. This is a pretty fun journey of, oh hey, we measured it, oh hey, it looks right, oh hey, wait, what? No, that's not right, no, stop, you're going the wrong way, crap, why do you get different numbers now? Shit, now we have a problem. Sometime around when I got here, it started to become clear that if you measure h naught in different ways, you get different answers. So we can measure h naught from the light from the Big Bang, that's this CMB business, and you'll notice that doesn't change very much until here. That's when the satellite WMAP happened. It went up and measured all these things. And then here, this is when Planck finally finished its data analysis, and the error bar got a lot smaller and the number went down. And as we refine our techniques and the data gets better, this gets better and better, and those error bars get smaller and smaller and smaller, and they get further away than if you do it with Cepheid variables. So Cepheid variables are these pulsating stars, and you can measure those pretty far out. If you measure the expansion with those Cepheid variables, you get this value, which is now statistically significantly different from what you get from the Big Bang. There's this other one, this is called the tip of the red giant branch, which we'll talk about in a little bit. But basically, when I'm doing this kind of thing, I need something that always looks the same. And it turns out that red giant stars get up to a certain peak brightness and then stop. But that peak brightness is set by some pretty fundamental physics that I don't understand well enough to tell you about. But the peak brightness is set by some fundamental physics that allows you to do distances with just the red stars, the big ass red stars. And they give you a number that's in the middle. That doesn't help. So the big difference is if this is the Big Bang, and this is today, the CMB measures things here, shortly after the Big Bang, and Cepheid variables measure things out to about here, the redshift of a few. So this is time moving this way. So we can look back a little bit of the way with Cepheids. We can look back a little bit further with the tip of the red giant branch. We can't look all the way back to the CMB. There's this huge dead spot where we don't know what's going on. We're hoping James Webb can fill in some of this. Oh, okay, now it's time to be done talking. How do we use this? I think I've gone through all of this. I'll talk about photometric redshift later. So we have this thing called the distance ladder. This is the last thing I'll say, and then we can part ways. So we can get the actual distances using parallax and binary stars. That's good out to, you can get binary stars, I think, in the LFC and the SMC. Get a little distance in the within our galaxy. So we use that to calibrate all the Cepheid variables. So we have some Cepheid variables that we have parallax to, and then we can sort out the relationship between the pulsating stars and actual distances. So that's the first rung of the ladder. So this is physics that we need to know, that we are bringing some physics to this measurement. Parallax, you don't bring anything to the measurement. You do the measurement and it tells you what the distance is. It just works. Well, okay. There's measurement uncertainties and stuff that you have to take care of, but there's nothing squishy or complicated. There's no thermodynamics in that. When you go to Cepheid variables, we don't understand the thermodynamics quite well enough, but we can calibrate, and that works really great. That gets us out a certain distance until we can't see the Cepheids anymore. But within there, we have all these type 1a supernovae, so we can use the Cepheids to calibrate the supernova. That gets us the next rung out in distance. So I don't think we have parallax to any supernova. I think it would be really problematic if we did, because that would mean the supernova was close enough for us to do parallax, which would mean the supernova is close enough to jack up the planet. So we need this kind of staircase of measurements that goes from the local universe out to the edge of the universe. And it works pretty good. So, and then the Hubble flow is how we get to things to very large redshift. Yeah, should I put up that other thing? No, I should just stop talking. There's so many things that are cool. I could talk all day. Does anybody have any other questions that they want to talk about? Everybody good? All right, so there will be